Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our 7th webinar of the season with Professor Michele Zorzi from University of Padova, Italy. Please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons, so please stay online. Professor Zorzi agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Ian Akyildiz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akyildiz is Ken Byers Chair Professor in Telecommunication Emeritus at the Georgia Institute of Technology. He has established many research centers worldwide, including South Africa, Spain, Saudi Arabia, and Finland. He's editor-in-chief emeritus of impact factor journals, highly cited and at the top of the most prestigious international rankings. Ian is visiting distinguished professor in many universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. Professor Akyildiz, the floor is yours to introduce our speaker and to moderate the Q&A session. Thank you.
Thanks a lot, Alessia. Distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you are joining us from across this vast and interconnected world. From the magnificent city of Istanbul, a timeless crossroads of civilizations and symbol of unity between East and West, it is with immense pride and profound excitement that I welcome you to the grand inauguration of the Season 4, Episode 7 of the ITU Journal on Future and Evolving Technologies in short form, ITU J-FET webinar series. Today, we are exceptionally privileged to host a true luminary, a scholar whose pioneering contributions have redefined the boundaries of wireless communications, Professor Michele Zorzi. Before we proceed, allow me to reflect on the transformative mission of the ITU J-FET. Since its launch in December 2020, the journal has stood as a global beacon of open access innovation, forging an indispensable bridge between academia and industry while democratizing the frontiers of cutting-edge research. Every submission undergoes meticulous peer review, ensuring that only the most visionary and impactful work shapes the future of technology. Meteoric rise of the ITU journal as a premier global publication owes much to an extraordinary team. Söze Ono-san, Bilal Jamusi, Alessia Magliarditi, Erika Campilongo, Maria Otero, and many others whose unwavering dedication has been nothing short of remarkable. To the brilliant minds in our global audience, we invite you to contribute your pioneering research and join us in driving the next wave of discovery. I'm also thrilled to announce that our journal has been officially indexed in the DOAJ, which stands for Director of Open Access Journals, a landmark achievement that expands our global influence and reaffirms our unshakable commitments to unrestricted knowledge dissemination. Now it is my privilege to introduce today's distinguished speaker, a visionary scholar, a forefront researcher, and cherished colleague, Professor Michele Zorzi. Widely regarded as one of the leaders in communication engineering, Professor Zorzi's transformative contributions span multiple generations of wireless technology, leaving an indelible mark on academia, industry, and beyond. Professor Zorzi earned his laurea and PhD in electrical engineering from the University of Padova, Italy in 1990 and 1994, respectively. His academic journey took a pivotal turn during 1992-93 when he conducted research at the prestigious University of California, San Diego. In 1993, he joined the faculty of Dipartimento di Elettronica e Informazione at Politecnico di Milano, Polimi. After 3 highly influential years at UCSD's Center for Wireless Communications, he returned to Italy in 1998, joining the University of Ferrara, where he was promoted to full professorship in 2000. Since November 2003, he has been cornerstone of the Information Engineering Department at the University of Padova, a testament to his enduring intellectual leadership. His current research spans mobile communications, wireless sensor networks, IoT, cognitive networking, 5G millimeter wave systems, vehicular networks, and underwater communications, each domain enriched by his innovative insights. Michele's excellent impact has been recognized with numerous IEEE Communication Society awards, including 2 Best Tutorial Paper Awards, 08 and 19, Education Award, 16, Stephen O. Rice Best Paper Award, 18, Joe Lo Cicero Award. He was a nice friend of mine. He died very early, unfortunately. He's from University of Illinois, Chicago, Joe Cicero, for his exemplary service to publications in 2020. Michele's editorial leadership is equally legendary, having served as editor-in-chief of IEEE Wireless Communications magazine from 03 to 05, IEEE Transactional Communications 08 to 11, and IEEE Transactional Cognitive Communications and Networking 14 to 18. So he served a lot at the Communication Society. They should be really thankful to him. Beyond publications, he also has shaped IEEE Communication Society as member-at-large of Board of Governors from 9/11 and 21-23, Director of Education 14-15, and Director of Journals 20-21. A fellow of the IEEE, his scholarly influence is further underscored by an H-index of 96 and over 97,000 citations, a testament to his monumental contributions. Now, my personal experience with Michele, I first met Michele in 2002, almost 23 years ago, when I was a postdoctoral research working alongside my esteemed friend, Professor Tony Acampora. He was the director of the CTR Center for Telecommunication Research in Columbia University. Then he moved to University of California, San Diego, early 2000s. Even then, Michele's pioneering work in wireless mobility and resource management revealed an extraordinary intellect and boundless curiosity. Over the years, our paths converged in remarkable ways, first in wireless sensor networks, then in the emerging frontier of underwater communications. As early as 2005, we independently envisioned multi-mode underwater devices. I'm sure he remembers that, a striking alignment that highlighted his visionary foresight. In March 2006, we served together on the EU Research Council Strategic Planning Meeting on Wireless Sensor Networks. You see, I remember those, Michele, helping shape the future of the European research in that domain. Since then, our encounters at prestigious conferences, workshops, and collaborative forums have been consistently inspiring. Most recently at BalkanCom 2024 in Slovenia, Michele delivered an excellent keynote speech. Michele is not merely an ambitious researcher, he is a true leader of telecommunications whose 2 decades of forefront work have set the very high standard in academia. His relentless pursuit of excellence ensures that his research remains at the vanguard of innovation. Dear Michele, today we are happy to have you here. Your insights will undoubtedly spark new paradigms, challenge conventions, and inspire generations to come. Ladies and gentlemen, please join me in giving a heartfelt welcome to Professor Michele Zorzi. Michele, it's yours.
Thank you, Ian. Thanks a lot for the very, very kind and many kind words you said about me. That's really, I'm really honored to be introduced that way. And so good afternoon, everyone, or morning or evening. So let me share my slides here. Okay, sorry for the glitch. So again, good afternoon, everyone, and thank you very much for the invitation. Thank you, Ian, for inviting me and introducing me. Thank you, Alessia and the team for the support you gave us. Thank you to the ITU and to you who are participating in this webinar. So the topic I'm about to talk about is non-terrestrial networks, which is, as some of you may know, an emerging area in the 6G landscape. Of course, satellite communications has been around for many decades now, and so it goes back many years. And at some point, it seemed that there wasn't much of a future for it, except for some very specific applications like broadcasting or things like that. More recently, there's been a big revival of this technology, which actually has been reinterpreted and recast in a much richer way compared to what it was before. And so what I'm trying to do here is to give you some glimpse of what this new landscape may be, how it relates to new research, how new challenges emerge as we look at different paradigms and different use cases and different technology solutions for this type of scenario, and its integration, with the 6G, which is the telecommunications. Now, I should mention that this work, so what I'm trying to do is to give some perspectives of some trends or enabling technology, make some of these vision true or at least reachable in the near term. Then I'll draw examples from the work done by my own group, not because that's the only work that's done or it's the best work that's done, but it's the work I know the best. And what I'm trying to do here is not to give you an exhaustive view of what exists in this area, but rather to try to give examples that show some of the trade-offs that emerge in this context, so that, by these examples, you may get interested in this topic. And, if among you there are students who are looking for good topics for their thesis or their PhD research, and I hope some of you may get interested thanks to what I'm going to describe in the next hour or so. Since this work comes mostly from my group, there are many people I have to recognize. In particular, in this slide, I mentioned Professor Marco Giordani, my colleague and former student, Alessandro Traspadini, who's a student who will graduate soon, Matteo Pagin, a student who just graduated, and many other members of my group. So I won't spend much time on the evolution of wireless systems. You know, we all know this generation path where roughly every 10 years, a new generation of cellular system is introduced. We are now in the middle of the deployment of 5G, which has been, you know, heralded by many as a disruptive change compared to the previous generations. So each generation, besides improving the performance and so leading to, in particular, higher and higher data rates, also has some distinguishing feature compared to the previous one. So from 1 to 2 was, you know, digital versus analog. 2 to 3 was some internet access instead of just voice and short messages. From 3 to 4 was full-blown data and internet. 5G introduced the paradigms of you know, broadband communications and also massive access and ultra low latency and reliable communications. And now for 6G, we're looking at a fully integrated digital world where artificial intelligence will play a key role, and where you know, we will serve many different services and use cases in a single complex and heterogeneous infrastructure that is being designed. And non-terrestrial networks is part of it. So as usual, and since this is sponsored by the ITU, this process of introducing new generations and new technologies has a path through standardization, which, you know, through groups and studies and discussions and consensus tries to build the rules and that define what a system should be. And this is a fairly long and complex process. So we are about here in this project. And so you know, the 6G has been studied for some time and will be studied even more, with the expectation of the being introduced in the market, at least initially in 5 years or so. Now, there is also a path for non-terrestrial network standardization, which is part of this. So this slide highlights that with some blocks, which you know, highlight some work items or study items that are being considered now. Now, Release 17, so this standardization process issues documents every so many months called releases, which are specifications where you know, some technologies are described. And Release 17, which was issued some time back, is the first that specifies enhancement for broadband services via satellite direct access to the terminal. And so there are some features that are mentioned. There are some use cases, both broadband and IoT. There is some assumption about location knowledge for users. It's limited to FDD, and we discussed that in FR1, which is sub-6 gigahertz bands. And so it was important to introduce this in the standards documents. And of course, follow-up releases 18, 19, 20 will included and will include other features that go in the direction of making this non-terrestrial component of the networking infrastructure more and more powerful, more and more flexible, by introducing facilities and functionalities to respond to users' needs. There are some documents from the 3GPP, which is one of the main organizations behind the standardization of this evolution of the cellular system generations. So I just, for your reference, put here some of the studies that refer to non-terrestrial networks. So NR is the name that is given to the air interface for 5G, and includes new technologies and innovations like the use of millimeter wave and some new waveforms and some architectural changes here. So use cases for 6G, there are many. You know, it's you know, as you can invent your own use case for this very high speed, high reliability, low latency communication system. Now, in the context of non-terrestrial networks, we started to get interested in this area based on the need for worldwide connectivity. Now, I was at the communication theory workshop last week in Venice, and there was a whole session dedicated to non-terrestrial networks, including a keynote by Professor Slim Alwini, and he made the following point. Many think that satellite communication, non-terrestrial communication, is motivated by worldwide connectivity, and to some extent, that is even true, right? But he gave so many examples of other use cases and applications that go well beyond just the need to cover rural areas. Applications related to smart city environments, applications related to flying vehicles for deliveries or even for people. And so there is a lot of interest in this, in bringing communications just up from just the ground and to cover the three-dimensional area with all the population of objects, vehicles, sensors, and even flying people who can inhabit that. And so I will be making reference to this worldwide connectivity application for a while, but please keep in mind that there's much more to it than just covering underserved areas, even though that serves as a convincing and quite adequate example to start this discussion. So if you look at the map of the worldwide coverage, then you see that some countries are very well connected, others are much less so, as you may expect. And so there are countries where really the penetration of internet services or wireless communications is very, very low, so close to 0%. So this is an issue from many points of view. Clearly, the business companies may see an untapped business opportunity where a service could be offered that it isn't so far. From a more humanitarian point of view, we recognize that people who don't have access to digital services are disadvantaged compared to others who do. And so in many of these countries, providing connectivity may go a long way towards improving the quality of life, improving the opportunities people may have in education, in jobs, in reaching a level of living which is much better than where they started out. And so there is both a technology challenge to make this accessible to everyone. There is also an ethical imperative, I would say, to make sure that we give equal opportunity to all the population of the world. And there's also maybe a business case that could be made, even though admittedly some parts of the world are harder to reach or to provide infrastructure to. They may not have the economical means that other parts of the world have, and so the business case may be harder to make. But still, with the creativity of researchers that can provide technology at low costs and maybe some business models that can be different, maybe there's room for some improvement in this map, and hopefully 10 years from now we'll look at a wholly different map. Now, having said that, even in countries that we consider economically advanced, there are situations where not everything is so good. So just to start from my country, Italy. So this is a map of the connectivity at 100 megabits per second, which is pretty good, right? Of course, green means good, well served. Lighter green means slightly less served. Red would mean not served. Now, if our demand goes from 100 megabits per second, which is almost everywhere available, to a higher, broadband connectivity of 1 gigabit per second, then we start seeing areas where this level of connectivity is not reached. So we are lacking there. And so there is need, especially in some areas which you can recognize as maybe the areas with mountains, where maybe the terrain is more difficult to cover or to build infrastructure, or maybe areas where that are economically disadvantaged, and so there is less of a business case there. Even in the US, if you look at the coverage at 100 megabits per second, blue means covered, as the legend says. If you go to 1 gigabit, then you see that there's a lot to be done here in many areas, and so we're not there yet. So clearly we are going in that direction, but there are challenges which are both technical and economical, and so we have to strike the right balance between these to do that. Now, the other thing is that, which also motivates, I think, non-terrestrial networks, is that 5G as it is now in its terrestrial component does not have the level of reliability that we would like from wireless applications, because it's vulnerable. Since it is a terrestrial infrastructure, it is vulnerable to anything that may hit the Earth, from natural disasters to human-made disasters, and things that may compromise the infrastructure. And so this is a problem because we cannot guarantee this. And I have a number of examples here, taken from hurricanes in the US, like this, which shows the connectivity in Florida, which drops dramatically in the face of a big hurricane hitting the state. Or we have an increasing trend, unfortunately, due to climate change, where the number of extreme events on the natural environment is increasing steadily during the years. And so clearly we are going in a direction where we should expect more and more frequently these type of events, which disrupt the communication infrastructure, besides disrupting the lives and then the property of many people. And so that's something to keep in mind. If nature was not enough, humanity does its own part with the wars that, unfortunately, as we see, continue popping up in different parts of the world. So here are some graphs of connectivity when the war in Ukraine started 3 years ago, or when the attack in Gaza was carried out. And so here, both because of what happens on the land, and because of maybe one of the targets is the communication infrastructure, then we have a lot of disruption in communication services in times where people need that the most, because both in natural disasters and in war scenarios, of course, people want to be connected and to let their relatives know how they're doing. They want information. And so this is something that is really a need, which is not well served as of today. On a happier note, we all are aware of situations, even in peacetime and in areas which may actually be well covered, where the extreme peaks of traffic may actually stress even the best designed network. And so when you have a lot of people all together in the same place and maybe all wanting to access digital services, then of course the network is unable to cope with it. And so we have lack of service. Now, the main reason why these problems occur, I relate these to two essential issues. Right? One is that cellular networks, as we know them today, have been designed with a two-dimensional service area in mind, so the surface of the Earth. Now, admittedly, there are cities where you have high-rise buildings, so it's not that everyone is at level 0, But still, that's not a full-blown three-dimensional space. And so exploring the three-dimensional space is a whole new business that needs to be addressed both by the researchers and by the companies for business opportunities. So that's one key thing that will be extended by non-terrestrial networks. Now, the other thing which is very important, I think, is that in cellular systems, in terrestrial systems, we have a very strong coupling between where the traffic is and where the infrastructure is. So essentially, we have base stations that are in the center or maybe in the corner of a cell, and so they're co-located with the traffic. They cannot easily serve traffic which is far away. And since cells are becoming smaller and smaller, this coupling makes the system very inflexible because you can only serve the local population. And if there are dynamics in these populations, you cannot easily follow them because you're tightly connected to a geographical space. Okay. And this is because we are on the ground. It's because the reach of these base stations is limited to a few hundred meters or maybe some kilometers in some cases. And if you think of non-terrestrial networks where network nodes are flying or maybe orbiting at some distance from the Earth, clearly their ability to illuminate a much larger area is there. So it's almost automatically provided. So it's almost given for free, right? And this is a real game changer because now you break this coupling between geography of the traffic and of the infrastructure. And so you immediately have very broad possibilities in terms of flexibility, in terms of reconfiguring a system to serve traffic peaks that may occur even at distance places from each other. And so this gives a tremendous flexibility and a lot of new possibilities to serve traffic, even in extreme dynamic scenarios, or even in with cycles where you have peaks moving around, or seasonal or daily trends that are hard to follow with an infrastructure of the terrestrial network and are much more easily followed here. And of course, the fact that these objects, these network nodes, are not on the ground makes them immune to some extent to natural disasters, earthquakes, floods, even war actions, terrorism. Of course, if someone wants to compromise a network, can always shoot a satellite, but it's clearly an order of magnitude more difficult than to compromise any infrastructure on the ground. So, for all these reasons, this new paradigm is very promising and very helpful, and so it has justly been promoted quite heavily in the recent years, giving new life to an area which seemed very mature and not open to additional innovation or to new horizons in its evolution. And so this cartoon shows a number of possibilities here. Clearly, some areas which are underserved by current systems, right, like rural areas or areas where the communication infrastructure is temporarily compromised, but also, hotspot areas providing ad hoc coverage in a given area which happens to be heavily trafficked in a certain time. Also areas which are difficult to cover by cellular systems, like maritime areas or offshore platforms. There are many things that can be done here with relatively few nodes, if you think about it, compared to the number of nodes that infrastructures on the ground have. Now, when you hear non-terrestrial networks, I guess most of us immediately think of satellites, but recently, you know, there's quite a diversity of platforms that can be used in this area. And in fact, I think one of the most interesting issues here is how to orchestrate these different platforms together into a common infrastructure where each type of node may provide different features and different capabilities. And so by using them together and leveraging on the strengths of each, you can provide a much better service to the user where, you know, we experience a wide variety of services that need to be coexist in the infrastructure, a lot of different use cases and applications, which you know, in the old days, we would build a system for each application. And then recently, we are converging to an infrastructure which is able to flexibly provide connectivity to most of the application and the services. So now we push in this direction of flexibility and reconfigurability, thanks also to the many innovations that have been provided, you know, in the communication landscape in the past years. So, you know, you can compare the platforms. And by the way, I have more slides that I can cover probably. And so I will maybe skip some, but, you know, I'm happy to leave the slides with the organizers. So they want to make them available to whoever wants to look at some details. Of course, that's a possibility. So UAVs is what we commonly call drones, which are very flexible. They fly very low. They can be deployed easily, but on the other hand, they have a small coverage and they have a relatively short mission time because the battery, so the propulsion energy is quite demanding. And so the battery cannot take this to fly for many hours. And so typically it's like 1 hour or so. HAPS, high altitude platforms, can be deployed at a higher altitude, like a few kilometers, for example, still fairly quickly. They can cover good areas because they're high. They tend to float, so they don't need a lot of propulsion, but to some extent for stabilization, they may still need motors and you know, stuff that try to keep them in place because otherwise they will be drifted due to currents. They can be solar powered. So these are platforms that are becoming popular and are being considered seriously for even ad hoc deployments of communication services. And then, of course, we have satellites, you know, the geo satellites, geostationary, which are, you know, 36,000 kilometers from the Earth, so they orbit together with the Earth, so they don't move with respect to the Earth, and so they provide continuous service. But of course, you know, the single most important issue here is the distance, which means, you know, a challenging link budget, which needs, you know, powers and antennas with some capabilities to be able to close the link. And it also means delay, which from the point of view of interactive communications and also networking protocol is clearly a challenge. This is mitigated by other orbits, so MEO and LEO, so at medium or low orbits, which on the other hand orbit, so they move with respect to the Earth and sometimes even quite fast. And so you need to deal with this mobility and you need to have multiple satellites to provide continuous coverage. And so there are networking and mobility management issues that need to be addressed here. Now, a typical non-terrestrial system, so there are many variations of this, but typically what you have is some flying platform, so be it a satellite or one of the platforms I was mentioning earlier, which ideally should be directly connected with a user terminal. And that by itself is already a challenge because if you think of, you know, what we used to do in the old days for satellite communications, there was a satellite and then on the ground, there was a huge antenna which provided the gain to close the link. Now we would like to have that into a user terminal, which is like a cell phone. which immediately raises the issue of how much power do you need to communicate to the satellite in the uplink, or how much gain can your antenna provide in order to be able to travel that long distance with your signal. So that's, easily said, but, it's clearly non-trivial. And then on the other side, this satellite or flying object will act as a base station of a bigger network. And so this can be connected to a gateway on the ground, which then is connected to a data network, let's call it the internet, okay? And so this is, and then you can have different paradigms. So the satellite could just relay the signal as it is in the so-called amplifying forward type of relaying paradigm, or it can detect, decode, and re-encode and retransmit the signal, which is a more powerful paradigm. And also it provides additional capabilities like communications between satellites. So you can have a mesh network in the sky. And so you can have, other possibilities that maybe the single satellite cannot provide. Now, use cases are many. So as I said, the motivating use case was rural communications, but there are many other possibilities, like which I mentioned earlier, like hotspot coverage, resource optimization. You can provide some additional infrastructure to cover for temporary peaks of traffic or temporary congestion in the network. You can provide Internet of Things service. So there is an emerging paradigm where you actually connect sensors or small nodes which need to send very few bits at a time, very infrequently, but there are many of them. And so this is another thing that is being promoted, because then the satellite ideally, is a very adequate platform because it covers a very large area. And so everyone who's in that area can send, and the satellite can hear all of them. And so this is a very good solution for massive access type of scenarios. We can have on board these platforms, maybe some mobile edge computing type of facility, so we can offload computation. Maybe you have nodes that are not as capable, and so they don't have the energy or the computational power to perform heavy computation, but they could delegate that computation to some more powerful processor, which may sit on the satellite, and we'll talk about that in one of the examples here. Now, I come from a networking background. And so for many years, satellite communications was essentially about closing the link and being able to send this signal back and forth from the Earth reliably. As soon as you make the system more complex, so you have multiple satellites, you may have multiple layers of satellites or objects at different altitudes. And these must work as a network, meaning that maybe the communication goes over multiple hops, not just a single hop. And so there are issues that relate to a multitude of nodes which affect each other in their behavior. So there are interactions, there is interference, and there are actions by some nodes that affect actions by some other nodes. And there is a protocol stack, so a series of algorithms that must work together toward the success of the communication system. And all of these depend on the specific features of the environment. And so here, on the left column, I'm listing a number of key features of non-terrestrial networks. One is that the motion of the vehicles for low orbit type of scenarios. The altitude, which relates to the distance from the Earth, and so the issue of link budget and delay I was mentioning earlier. The cell size, which is big, which is good in some sense, but maybe challenging for other aspects. The propagation channel, which is, since if you go to a satellite, you go through the whole atmosphere, and so the type of impairments you encounter are different than what you have in a terrestrial system where the base station is maybe 100 meters high, okay? And then a spectrum, because the satellite environment or the space environment is populated by many services which are regulated. There are bands that are assigned to some services for surveillance, for weather, for sensing, and all these are there and have their own life and their own importance. And here we are sending out in space signals which may interfere with these services. And so we need to pay attention to the regulatory constraints first, and then to see if we can find ways to coexist with these services without interfering too much. And so when you look at how these features impact on the stack of the protocol here, there are many things that need to be optimized or sometimes even redesigned, because when you have a much longer delay, then some protocol will just fail because they're not designed to deal with that type of delay. And so we need to find new solutions. We need to maybe go for different approaches than we usually use in terrestrial networks, which is by itself challenging because we need to be creative and find new solutions. If then, as is one of the current trends, we want the non-terrestrial network and the terrestrial network to interoperate and maybe even integrate with each other, then of course, if we have a mismatch between different solutions in the two environments, then we need to deal with that and find a way out of this. And then more specifically, we have that the propagation delay, for example, will affect ARQ mechanisms because the buffers needed are much bigger. Then you have issues related to MAC protocols. Those of you who are familiar with random access will know that if the propagation delay is large, then these protocols don't work. And so this is something that even scheduling, it's harder to do here. And so we need to find solution, which on one hand, it's challenging. From the researcher's point of view, is actually very nice because you have many problems that need to be addressed. And so there's a lot of work for researchers, PhD students that can spend many years working on these topics. And so research questions that one may ask are, how do we plan the network? How do we manage the network? How do we design the protocols? Can we optimize those we have? Do we need to completely redesign them? How about energy efficiency? Anything that is not connected to a steady energy supply, and of course flying nodes are not, except for maybe getting energy from solar panels. Then you have to pay attention to the energy issue, not just for sustainability, which should be everyone's concern, but also because you only have a battery which has so much energy, and so you must be very careful about how you use it. Then in this architecture, we have to decide where to position the different functionalities in terms of communications, but also in terms of computation, for example. And so there are optimizations there to be made. Sustainability, both environmental and economical. How do we develop this network in a way which is, mindful to the environment and also can provide a sound business case which allows the service to exist and not to crash. And then, as network designers, of course, we need to understand whether this works and what is the performance of this system. And so we started out observing, what we have in this area. And so we have some enabling technology. So it's not just by chance that this trend towards non-terrestrial network is happening now, has been happening for just a few years, because we have a conjunction of different technologies that matured and made this paradigm possible, which it wasn't before. Right? So one has to do certainly with antennas, materials, and electromagnetics studies. So this is both from the electromagnetics and materials side, and also from the signal processing side, which allows, amazing innovations like MIMO communications, which allows, huge gains there, but also beamforming and the possibility to create multiple beams, like in this picture down to the right, where you can have small beams that may cover small areas simultaneously, and so you can provide a cellular-like service there. So I'm not an antenna guy, but it's good for a network designer to rely on these abilities to provide coverage and connectivity and gains, so that we can rely on robust communication there. Now, a second important issue is that of spectrum. Now, if you deal with radio access networks, then of course you have to deal with spectrum issues. And this picture at the bottom is probably the most widely used picture in all presentations ever, which is the allocation of spectrum in, I guess this is in the US, but almost everywhere is the same. And so you see that there is a lot of occupancy, and all the spectrum is assigned to some service, because it's a very precious resource. And so everybody wants a piece to implement a service. And this is a problem because there is no room for anything else almost. And so one of the big things that was promoted in 5G was the use of millimeter wave spectrum. So traditionally, cellular systems work up to initially 2 gigahertz, maybe then up to 5-6 gigahertz. But then there is a lot of spectrum which is there, and it's not used for terrestrial communications mostly. There may be a lot of other applications in the military area, in the satellite area, or scientific services. But by and large, there is a piece which is called the millimeter wave band, which technically goes from 3 to 300 gigahertz. But some of these bands have been identified as very promising for service in 5G communications, and some of them has been used or proposed for satellite communication as well. So what's special about this? Well, what is special is that there are bands available, and their size is also quite good. One of the major boosters for throughput in networks is the availability of spectrum. If you have access to large spectrum, then you can hope for very high throughput. That's very easy. Okay, so that's why we want to go to millimeter wave. What is hard about the millimeter wave is propagation, because the laws of physics work against us to some extent. And so propagation is more difficult. The attenuation is higher. There are effects like blockage, where some objects cannot be passed by these signals, whereas at 2 gigahertz they can. And so, for example, going from outside a building to inside a building is much more challenging here. And so you have to, provide alternatives. So the good thing about millimeter wave is that since the wavelength is so small, then you can pack many antennas in a small physical space. And so you can boost your signal by antenna gain, which depends on the number of elements. And so if you can pack many in the same space, then you thereby have a gain there. And so you can compensate for this additional attenuation. What is harder to compensate for is the blockage, because if you have an object which obstructs your path, then you need to go around. There is no way you can go through. Even if you boost your power, then it's very hard to penetrate. And so this calls for maybe some network deployments which are more difficult or bigger. And so this is something that is being studied. And so the use of millimeter wave is there. And if you go to space, then you have some effects which are not there in terrestrial networks, in particular tropospheric scintillation and atmospheric absorption, which need to be taken into account when you do your link budget exercise with one node which is far from the Earth. And so we did that. And so what we wanted to do was, because the main question is, can it even work? Because if millimeter wave only works on short distances. That's one of the lessons we learned from 5G research. Well, then satellites, by definition, are not at a short distance. And so is it possible? And one may say, well, millimeter wave have been used in satellite communications for many years, but then, again, this was done with huge antennas on the Earth. And so this is not what we're talking about here. What we're talking about here is satellite to a handset, which then doesn't have the antenna gain that we expect from ground stations of satellite systems. So the whole new game, right? And so this picture shows the capacity you can achieve for a certain frequency and with some antenna gain. So clearly, when you go up in frequency, you have several effects, right? One effect is that you have more bandwidth. Okay, so a typical channel at 2 gigahertz, maybe 20 megahertz. If you go to millimeter wave, then you can have access to several hundreds of megahertz or even a few gigahertz. And so this provides more throughput, but then propagation is harder. And so you have conflicting effects. And that's why, if you increase frequency, initially you go up in capacity because, the additional bandwidth helps you. But at some point you flatten out because then propagation starts kicking in. And so the difficulty of closing the link makes your throughput suffer. So it's not necessarily a monotonic behavior. This is antenna gain. Of course, 200 dB is ridiculously high, but it's just for the sake of discussion. You see, we can reach tens of gigabits per second with reasonable parameters. And so, yes, even for geos, which are far away, from the point of view of closing the link and providing sufficient signal quality at the receiver, we can do it. And so that's good news, even though it has to be done carefully, obviously. Now there are different parameters you can study. So you have, for example, the elevation angle. So the elevation angle is how high or low the satellite is on the horizon. So a low elevation angle means a low satellite. 90 degrees means just perpendicular. So it's over the top of your head. And there is a strong dependence on the elevation angle because if you have a satellite which is low on the horizon, you have two effects at least. One is that you have more objects, more obstructions, because if you're low, then you may have buildings, trees that are in your way. Number two, if you think of the atmosphere as a band of disturbances or attenuation around the Earth, then if you go out perpendicularly, then you go for the minimum distance. If you go out, grazing the Earth's surface, then your path through the atmosphere may be much longer. And so you're subject to the attenuation effect due to the atmosphere for a much longer trajectory or much longer distance. And so this provides additional attenuation there. And so this is what these pictures show. And then you can see that, again, as you go up in frequency, initially you gain, and then at some point you tend to lose because of the effects I was mentioning earlier. You can compare rural versus dense urban. Of course, in dense urban, especially for low elevation angle, you have a lot of obstructions, and so the throughput tends to be much lower, whereas in rural areas, which are typically more open, even though they have trees, you can have better performance there. Now, a third area is that of architecture. Now, there are many aspects to architecture. Clearly, one thing is, these new generation of satellites, which are very small and can be launched more easily. And, Starlink is there for everyone to see, how cheap has become to send satellites into space. And so that's a game changer. Another game changer is the software-defined networking paradigm. So you can launch satellites and then you can reconfigure, you can slice, you can adapt even after they have been launched. And so this gives tremendous flexibility and a possibility to optimize continuously. And then there is heterogeneity because you have many different elements. And as I said earlier, you can make them interwork in some optimal way. And so this would be, a very important optimization exercise and very difficult optimization exercise. So just to give an example of how this can work. Let's compare this. So let's say you want to communicate with the geo satellite, which is the farthest that you have. And let's say you can do that in several different ways. One is you go straight, right? Just one hop, go there, which is the most difficult because it's the longest distance, right? Or you can break the link with a LEO relay, or maybe a HAP relay, or maybe both. Okay, and so we want to compare this solution and see what happens there. Now, in doing that, we refer to a 3GPP document which specifies the parameters of this system. And so I don't claim you can read or even want to read this, but just to show that there is some solid ground here from an international entity which specifies the parameters. And so this is what we find. Okay, so this is the capacity, so how much throughput you can expect as a function of the elevation angle, as I mentioned earlier. So you expect that the performance improves as the elevation angle increases. That's fine. That's what we see. But then if we compare different solutions, you see at 2 gigahertz. So the direct communication to the geo is the worst because it's the most difficult. It's the longest distance, right? If you break the link with the LEO, then this is what you have at 2 different altitudes. If you break with a HAP, this is the darker blue curve. And then if you have 2 breakpoints, you have this light blue. Now, what's interesting is that the HAP relay is the best. And here's why. Because if you had a uniform link, and you broke it into 2 pieces, so convexity arguments would tell you that the best is to break it exactly in the middle. But we don't have a uniform link because the part close to the Earth is much worse than the rest. So once you're out of the atmosphere, you have a clean channel. And so breaking in between is not the best thing. In fact, the best would be to break it within the atmosphere, because then you spread the pain of the atmosphere between the 2 pieces. And so that's what HAPs do. And so that's what motivates this behavior here, which becomes even more severe if you go up in frequency because of the different effects that come into play. So in this case, the LEO solution may actually be worse than the GEO solution, which is interesting. And actually, we could have a discussion about that, but we don't have time to do that. Okay, so that's basically the type of studies, architectural studies that we made here. And so if you want to put the performance of this system on a 2-dimensional graph where you have outage probability, so the probability that some level of service is not achieved, and on the other axis you put the capacity, then where you want to be is in the lower right point, because that's where capacity is high and outage is low. So you see that how the different solutions position themselves. And so the working point to choose, which is the one which is closest to this point, is the relay with the HAP, which is consistent with what I just discussed earlier. Okay. Now, one example which maybe I'll skip is the IoT Smart Cities example. So what we would like to do here is to compare different solutions for IoT applications. And, some potential technologies, Sigfox, LoRa, and narrowband IoT are there. And so the, one may wonder, what works best in this environment where sensor communicate directly with the satellite. And this has to do with, the type of signals we use, the robustness of this signaling, and the interference characteristics. And so we did some study and we obtained some results here, which show basically that if you want to apply this to satellites, LoRa may actually be the best solution. So Sigfox is a clear loser. Narrowband IoT, which is the main contender to LoRa, can work well with lower platforms, but for satellites, it's not working well because LoRa is more robust as a waveform. And so this is what motivates this environment. So we did some studies here to compare that and to provide some solutions here showing this result. Now, another interesting problem is how to use platforms for computation. Okay, so here's the environment. So we had a vehicular scenario in mind. And so vehicles may have limited computation, and so they may rely on the higher computation on platforms, let's say a HAP. And so here are the possibilities you have. You process everything locally, and so you have lower computational capacity, which means it takes longer for you to process. If you go to a platform, then you have higher computational capacity, and so it takes less time to process, but of course you have to send the data there and get the reply back. And so there is some transmission and propagation delay, which needs to be included in the delay budget. And so processing time goes down, but you add some more transmission or communication time. And if you go even higher to a bigger node, like a HAP, you have even more computational capacity, but even more transmission delay. So where's the optimal point? So that's a very well-defined optimization problem. And you can solve this. You can cast the problem mathematically. You can solve it in some way. And you can provide the optimal offloading factor, for example. And so you see trade-offs which are easy to understand, right? If you have a lot of nodes that need offloading, then it becomes less and less attractive because there'll be a queuing bottleneck because many try to access the same resource. And so you'll spend most of your time waiting for service. And so you may be better off actually to process locally because then you don't incur that. If instead you have a good response from your computational resource, then it's better to send them the data to be processed and have it back. And so there are several interesting trade-offs here that you can play with in terms of different parameters, computational capabilities here and there, number of users, and things like that. And so this is another study which I think was interesting. So the last example I want to make has to do with a trend which is very popular these days, which is that of trying to introduce TDD in non-terrestrial networks. So TDD and FDD are two ways to do division duplexing, which means how to distinguish the uplink from the downlink. So frequency division duplexing assigns two different frequencies to the two directions, okay? And this is good because it splits completely the two directions, and so you can control interference very effectively. On the other hand, TDD, so to divide this in time, which means uplink and downlink use the same frequency at different times for the two directions. This is a trend which is there very clearly for terrestrial networks because it's cheaper, it has many advantages in terms of flexibility, lower costs, frequency diversities, and all that. The problem is that for non-terrestrial networks, this is hard because one thing you need to do in time division duplexing, when you switch from one direction to the other, you need synchronization. And this becomes hard when you have long propagation delays or long uncertainties in the delays. And so here's the problem statement, right? The satellite sends a downlink message. This downlink message reaches different users at different times according to the propagation delay. And then these users reply, and these replies that should be synchronized at the satellite, in fact, are not because there is this different delay. So people have come up with the compensation mechanism. So if you estimate the propagation delay, you can compensate by introducing some time advancement so that at the end, all these uplink messages get there synchronized, which is what you want to achieve. Of course, you see from this picture that there is a lot of empty space, which means that the bandwidth of the channel is unused most of the times, which is very inefficient. So that's the main problem. And this is as inefficient as, this delay is large. In terrestrial networks, this delay is zero essentially, and so there's no inefficiency. In satellites, the inefficiency will be very large. So what can you do? Well, you can increase the length of this uplink message so that you use the bandwidth better, but that's not very flexible. Another thing you can do, if some condition is verified, you can send a downlink message, and before you get a reply, you send another. And if timing is right, you can interweave these messages so they never overlap with each other. Okay, so it's a nice optimization exercise where you satisfy some conditions and then you can make this more efficient by introducing more messages in the same time frame without interference. And so this is what we did essentially. We proposed this scheme called ESSA, just to show you some example results. So this is the average channel usage. So the gold bar is the traditional system, and the green bars are the proposed system. And you can see that is significantly more capable in terms of throughput than the original system because it promotes this better usage of the bandwidth. And so this is essentially what this gives. So in terms of open issues, I have several slides for the different topics, but let me not go to them. Let me just use this summary diagram here, where I list a number of issues that are still open, and many of these I mentioned already. So channel modeling is an issue because we need to characterize the channel well, and this there are a lot of studies on the terrestrial channel, which is very well understood, but the air to ground, ground to air, or even air to air channel is much less understood, and so we need data, we need studies there to characterize it. Spectrum coexistence, I mentioned. So we need to find ways, and a lot of research on cognitive radio and cognitive networks that has been done in the past 20 or 30 years may become helpful here. So we can use some bands where other services exist without disrupting those services. There's a lot of things to do at the physical layer, like waveform design, synchronization, ARQ, TDD, I mentioned. So there are many issues there that need to be addressed. For access, clearly random access is a problem. How to decide where to connect, right? Because if I decide to connect to a given node, typically I connect to the one which is best for me, right? The one where I have the best channel. But that may not be the best from a traffic point of view, because maybe behind that node, there is a congested link. And so I think I connect to the best node, but in fact, it's the worst. And so you need a network perspective, not just a single link perspective, which is more complex and needs more information. Then we need to manage the constellation, so mobility, coordination, handover. The Starlink constellation will have eventually tens of thousands of satellites, which by itself is a challenge to manage. Architectural issues, security, higher layer protocol issues. Again, when you go higher in the protocol stack, some problems escalate, right? So the effect of delay, for example, on a protocol like TCP at the transport layer may be dramatic. And so even some small issue at the physical layer may actually amplify a lot when you go up. And so you need to design carefully. And we did a lot of work in that area as well to understand these problems and provide. And then computation, I mentioned. And so these slides are the ones on each issue here. One last thing, we are one of the main developers of NS3. Together with NYU, we proposed the millimeter wave module, and then we proposed many modules of NS3 to simulate different scenarios like automotive and others. And lately, we have provided also the NTN module, which everybody can use. This is an open source simulator, which and so we like, if you're interested, we'd like you to try it out and see it. It has all the functions that are needed to deal with orbits and with the satellite movement and the curved surface of the Earth and all that. And so it's a nice feature here. And so to conclude, let me just put up again this table of features and challenges as a reminder that this is a rich area for research. And I hope many of you will be interested and will join the effort in trying to make these systems more and more efficient and more realistic in the near future. And with that, I think I went a little long, but I'll give you back to Ian for the Q&A session. Thanks a lot.
Thank you, Michele. Excellent presentation. Also, some of the audience members already wrote that they loved your presentation.
Thank
So
you.
there are a couple questions, but I will start and maybe we'll get some more and then we can continue our discussion. Audience, please use the Q&A box and for your questions so that we can read them and answer them. So when I mean, you remember we discussed this also in Slovenia. So when the old timers listen to the talk, and they will say, okay, so we did all of this in 90s and 2000s, and now again talking about non-terrestrial networks and what will be the real challenges, because all these things that you mentioned, it was done before, like mobility management, aero control, MAC, and transport, everything, right? So what I missed is that actually you mentioned this, maybe the audience missed it, that there are new applications like teleport systems, like holographic type communication, like e-health, real time. So the biggest challenges nowadays are the latency problems and the bandwidth problems. So now talking about those, so the end-to-end latency is a beast, as you know, like especially when you use satellites, even for the LEOs, like 25 millisecond propagation delay up and down, like 50 milliseconds. And the GEOs are much higher, 271 milliseconds. Even if you use the CubeSats, they're also like, you know, at least 5-10 milliseconds they add. So now the latency is a beast for those applications you mentioned in the beginning, and they are also, you know, hot applications in 5G and 6G, as you know. And the other thing is about bandwidth. The bandwidth is like when you use, even you mentioned a lot about millimeter waves, they're welcome, but in fact, millimeter wave bands are also limited. We have seen that it didn't take the wildfire that not everybody is using millimeter wave bands. Now everybody is talking, you know, all these things, but I'm just repeating. They're going to the sub-terahertz and terahertz band. We had a speaker like a couple of weeks ago. He talked about terahertz band. So, you know, from those perspectives, then all those challenges become very hot topics, as you mentioned, right? I mean, all these, you know, error controls and MAC protocols, transport layer. But now it's not easy to answer, but I'm still asking you, in terms of grand challenges, end-to-end latency, as well as high bandwidth problems, what do you think, how can we solve those grand challenges? It's a little difficult question,
Yeah,
but
let me throw out some things, and then, you know, this is not clearly a complete answer or a definite answer, but at least some ideas. So something that differentiates these applications from what was done in the old days, well, one is that, you know, this is internet access, right? So everyone may want its own traffic. It's not broadcasting like TV or something. So, and that's where the need for bandwidth comes, not just because the single application needs a huge bandwidth, but because you have many users who want different things at the same time. And so that multiplies the bandwidth needs dramatically. Another key differentiator, I think, is the fact that we want to deliver these services to the handset, which wasn't there before. Before, either you had these you know, huge ground stations with the very large antennas, or you had specialized handsets with, you know, this antenna which would stick out, and that was designed to be connected to satellite. So the vision now is that we don't even know that our cell phone connects to a satellite instead of a terrestrial base station. And this is a huge problem because, you know, with the hardware we have, the power we have, and the antennas we have in a handset, thinking of connecting to a very far satellite is not trivial. And so this is something that, besides the transparency of the user experience, right? And the fact that the system should switch from one to the other transparently, but that's fine, we can do that. But being able to connect so far and you know, in a way that doesn't fry your brain because it sends out a huge power, or drains your battery in just 10 seconds because it's consuming a lot of energy. That is a challenge that needs to be addressed. So in terms of differentiating factors from what we did back in the old days. Now, clearly, delay is an issue, latency is an issue, but unfortunately, that's one of those things that it's a law of physics. So we can't break it. If the satellite is far, it takes long. That there is no way around that. Maybe predictive systems can help. So if we can predict well what's happening at the application level, then we may compensate for some of this delay by learning and trying to anticipate. So we don't wait for the information to actually come, but we know already what will come, and maybe we confirm when it comes. And so this may mitigate a little bit the latency problem by using heavily artificial intelligence. That may be an area where artificial intelligence may actually help. Now, in terms of bandwidth, one issue that I didn't mention maybe clearly is that having good or large footprints in these satellite systems is good because it gives you a lot of flexibility. You cover a large area, but then the issue is that in this large area, typically there are many users. And so collectively, they may produce a traffic demand which greatly exceeds what you have. Now, one possibility is to use spot beams, so you can multiply using essentially a cellular type of approach. But that in the downlink needs a lot of energy, because if you multiply the spot beams, then you multiply also the energy that you need. Or you can have many satellites, but of course, this was also mentioned at this workshop I was last week. If you compare the number of terrestrial base stations versus the number of satellites, it's like 3 orders of magnitude difference. And so you cannot think that you can cover the world with satellites and replace the cellular network. And that's also an answer to those operators that feel threatened by the satellite or the Starlink. Well, there's no way the Starlink can replace cellular operators because it doesn't have the capacity, right? So it's more like, you are trying to integrate these systems. And so whenever you have a good terrestrial infrastructure, by all means, you use that. You don't want to go to satellites. And you try to use satellites only where really there is no other viable or economically feasible solution. And so hopefully at the end, we'll have an orchestrated system that can provide the best user experience to everyone.
Yeah,
so that's...
I think it really depends on the applications,
right.
And to decide in which cases the satellites or these LEOs for inter-satellite links, etc., are used in order to combat the latency problems. Is really depending on the applications, in my opinion. And also, as you said, you can do some machine learning algorithm based protocol, new intelligent protocols, like in terms of routing access, and also like intelligent beamformings. So there are many ways of, people should try to solve these problems. There are many research problems that...
and we must even accept that sometimes, there are things we cannot do, right? I mean, if you want a certain performance in terms of throughput, the only way is to have a fiber to your home.
Yeah.
It's expensive. Okay, that's it. Either you pay or you don't have it. You cannot, I mean, there are some things that we must also be able to recognize our own limitations and what technology can do and what it cannot do.
Okay, there are more questions, so let me
sure.
start to ask them. So I will just randomly pick them and ask them. Robert Jondane is asking about the spectrum constraints and channel impairments, and how will you handle the interference issue and spectrum access? Actually, you talked about it, dynamic spectrum access or AI machine learning based accesses, right? So that's like from the cognitive radio networks learning, and then
that would be the first approach
AI
that comes to
machine
mind,
learning
right?
and solving the problem, right?
Right.
But then there is another problem again. If you want to say something, but there is also a problem about orbital congestions. Like I added this now, like mega constellations like Starlink, OneWeb, you mentioned about Starlink, there are also collision risks and coordination complexity. So not only spectrum access problems, but also like these physical collision risks, you know?
Yeah.
What do you think about those?
And that was also discussed recently. You know, there is, of course, the more things you put in space, of course, in theory, you can predict all the trajectories and everything, but yeah, it actually, it happened that some satellite went out of its trajectory and some Starlink satellite actually was about to collide with something else, which fortunately had some control. So it could shift its trajectory and avoid the collision. And the big thing about collisions is not just that, you know, two nodes may destroy each other, but the effect of that collision is to scatter many smaller pieces, which may hit other devices. And so you may start an avalanche effect where, you know, you produce debris, which then causes even more collisions. And so this is actually quite a concern there.
You know, in year 2000, there was an article in USA Today, it's a newspaper, like 25 years ago. It was talking about trash of all the satellites in the space. And the United Nations was trying to find a way of cleaning them. And there are many countries, they put their satellites up there, and when they die, as you know, they are like 7 to 15 years lifespan, depending on the satellites. And they didn't clean them. You know, I don't know what's happened in the meantime. Do they have regulation? Are they cleaning up? Is it still trash there? I don't know. But so Diego Tutsi, Universität Bundeswehr München. I visit them many times. My friends are retired there now. So he really mirrors my thoughts and also my statements. He says millimeter waves has not been successful in 5G from a deployment perspective. There are not too many base stations and terminals and smartphones. Do you think there's a future for millimeter waves in the non-terrestrial networks for direct access?
Well, there may be. I mean, the millimeter wave was pushed in cellular system, and you know, our mutual friend Ted Rappaport pushed it very hard. And it made a convincing argument, and many bought that argument, but then the market was not. And I think part of it could be because the actual benefit you get from millimeter wave is not there, meaning we don't need yet that much bandwidth, and so there is no desperate need to implement, and so that just didn't happen. Right?
Exactly.
Now, it depends if in the satellite environment, if you know, millimeter wave is really a game changer and it allows to do things that you cannot do otherwise, then of course it would pick up. Okay? Plus, millimeter wave has been used in satellite communications already, right?
Yeah.
But
again,
the difference was that it didn't go to the direct terminal, but it went to ground stations. Right? And so
he has a point, Michele. So it didn't take the wildfire, you know, because to my knowledge, when I started to, you know, conduct research, I realized that time, it was at least 18 years ago. So the real bandwidth, I mean, the usual bandwidth of millimeter wave bands were like 7 gigahertz useful bandwidth. So that's why I said, why don't we go up to terahertz? And that's why I started 2007. I went to the higher bands. And and unfortunately, these millimeter wave bands didn't do whatever they were supposed to, or whatever. You know, Diego has a point here, but you know, it depends again. People, So anyhow,
but I want to mention that, you know, many of the things I talked about today don't have to do directly with millimeter wave. Some
of course not. No, Michele, I'm not
specific
saying
millimeter wave.
No.
But many issues are still there, even though you go to lower or higher bandwidths.
Absolutely.
I take the point that, you know, maybe the study of millimeter waves is of academic value, but maybe it doesn't find application, at least immediately. Yeah.
I don't think that it is understood that you are advocating millimeter wave bands. It's not. Please, you know, don't think so. It's not the case.
No problem. No.
So there is Marco Carugi. He's from Huawei. He says, thanks for the excellent presentation. Thank you also, indeed. He has two simple questions. Beyond ongoing research and open issues, what are the main standardization-related issues? If we can say at this stage we are facing, and if solved, will increase the market value of the solutions. And then what are the major contributions expected from AI with respect to the key? Well, that's too long question, Marco. So I think we should, can we do this offline, the second part? Because there are a lot of issues talking about AI, right? So Michele can give you another talk if you want.
The standardization, I think, is moving, right? The standardization,
yeah,
and clearly, you know, the spectrum regulation is one issue that has to do with standardization big time, right? Other than that, you know, I think how to map NR, for example, to the satellite. So how to drive the standardization using sound research result and good arguments. That's a challenge, right? Because many changes are needed.
Actually, you also presented very well these releases 17 and 18 about the NTN support.
Right.
And maybe the 6G integration requires some more harmonization, but overall it's, you know, pretty well defined. And for ITU and national regulations, maybe still open, like spectrum allocation, orbital slots, and drone flight restrictions. That's a big problem, as you know, drone flight restrictions and drone spectrums. They vary globally, but you know, these are all issues that needs to be addressed. Marco, I really apologize for the second question, but you know, it will be long to answer, right, Michele? I don't know about all these AI issues, but maybe Michele can write a paper on this for you.
Yeah, with Marco.
So that another question is about Lorenzo Luini. And he said in this slide, he didn't put the number, but I remember this slide number 39, as I can recall. I hope I'm right, Lorenzo. I would like to ask what attenuation levels were considered.
What?
Attenuation levels, attenuation.
Oh, okay. Well, we took from the 3GPP documents in terms of you know, the attenuation is calculated using that simple model where we have the basic path loss, like Freeze equation. Then we have penetration loss if we go through any wall. And then we have the scintillation and absorption. And for those, there are models that have been proposed, parametric models with measurements that fit the things. And so we just used simple models which are widely available in the literature. So we're not experts in physics of space or anything.
Right.
We just found in books or papers some easy to use formulas, and we use that to make the computation of the link budget. It's little more than a back of the envelope calculation, actually.
There are many other statements by the audience. They loved your presentation. They thank you. And I also thank you for this excellent presentation and also Q&A session. And dear Alessia,
okay,
you can take over. And Alessia
Thank you, Ian.
doesn't share her questions beforehand, just to let the audience know. So nothing is prepared. So there will be spontaneous questions, and she expects spontaneous answers. So again, thank you, Michele.
Thank you, Ian.
We'll
and
be in
goodbye,
touch.
everyone. Thanks for enjoying the
Ciao.
presentation.
Ciao.
Okay, bye.
Thank you very much. So let's move to the Wisdom Corner, live life lessons. So don't leave us. So I would like to ask a few questions to our speaker. I would start with my first one. So looking back on your journey, what is the most valuable life lessons or even a failure that you have encountered that shape your path? And how can this lesson inspire or guide those attending this webinar?
So I think one characteristic of my professional path, at least compared to traditionally what happens in Italy, is that you know, I was open to challenges and not afraid to leave the country, go to different places, work with different people. And so taking the challenge ultimately has been very fruitful. And so I would encourage everyone to, you know, not be afraid to go out of your comfort zone, to challenge yourself and to push, because if you really make a big effort and are not afraid to take up challenges, I think that pays off at the end. So that, especially for research, I mean, this is very, very important to know different people and work with different people and listen to many people and talk to many people. So I think that's really
Thank
good.
you. So you answered my second question. That would be which qualities you would recommend that students have, like be brave, be open to new experiences. Okay, and I
I
would like
may
yeah,
also
please.
give another controversial advice, because unfortunately, the system in which we work globally pushes us to do things in a certain way. Publish like crazy, publish more and more, publish quickly, and get as many citations as you can, which is often goes against well-done research and thought process, which is complete and which is thorough. So sometimes, I mean, I would be a fool to just tell people, don't pay attention to these things and try to do good research, because that would be, a killer for their career. But at least some time try to devote to something which is really profound, which is challenging, which is long-term. Don't be satisfied with just short-term results, which may pay off immediately, but then if you want to be remembered, then you want to do something big, even if it takes 10 years.
Yeah, fair enough. Thank you. And what actually first inspired your passion on your field? And how did you turn that interest into a meaningful career? So going back to when you started studying.
Yeah, it's interesting because I started out to be a power engineer. So I started my studies to study, electrical machines, electrical plants, and that type of thing. And then it was actually satellites which drew my attention. And so after 3.5 years of university, I switched to electronics and to telecommunications. And so that, because I was attracted to this, the communications field, but I think what sparked my interest was actually a fascination to satellites and space. And then, at that time, it was easier, I think, because it was a time where communications was booming, because wireless communication, I was working in wireless communication. And of course, when we're starting seeing, digital systems for wireless communication, cellular systems were in their infancy. I mean, I was already a professor when I first owned my first cell phone, which, like now babies have their cell phone.
Yes.
And, cell phones didn't exist when I was a student. And so, making a career in this area, the internet on one side, all these digital services, wireless communications. So it was a very rich field. And so it was, now admittedly, the interest in some of these issues has decreased, because some of these fields are seen as mature, and so maybe not so exciting. But then every once in a while, something else comes up or pops up, and so one of the purposes of my presentation was to say, hey, there is something interesting happening here, even though maybe you read on the newspapers that telecom is dead, or I know for a fact that telecom engineers are in demand, in great demand, and COVID has taught us that communication systems and virtual reality, teleconferencing, access to data, high-speed connectivity is invaluable. And so this shows that telecommunication is not dead. The challenge for us researchers is to avoid that telecommunication becomes just a commodity, which is very widespread and very useful, but not very valuable. And we push the envelope so that we create new challenges and new services and new systems, new technologies, so that we can keep the the area alive in a way, and we keep providing better and better services and technologies for humanity in a way, because that's what research should be for, right? It should be to make the world better and to make life easier and more productive and more enjoyable. So if we do that, then we succeed. If the technology and research only makes money to some people, then I think we failed.
Yeah, absolutely. Thank you. My last question. Among your career achievements, is there one particular contribution, whether professional or personal, that has had a profound impact on you or on others? And what makes this accomplishment especially important, meaningful to you?
I think one of the most instructive and meaningful experiences I had, I mean, it's hard to choose, right? So let me mention two things. One was my experience as editor-in-chief of the Transactional Communications.
Oh.
So Ian was pumping up a lot in my experience in editorial work, but really it was a change in experience because, first of all, I knew many people, and I was in touch with many contacts. I learned a lot from authors, from reviewers, from other officers dealing with that. You understand how the publication world works, how you can make it better, what are the weaknesses. And so that was really very interesting. And a lot of people tell me, oh, that must have been a lot of work. Oh, you're lucky you're finished. And actually, I did enjoy it. And so that was a nice 4 years I spent doing that work. Now, the second thing I want to mention is that, working with students is obviously a very fulfilling part of my job. I graduated now more than 50 PhD students, and so
Wow.
I have quite a descendants, and many of them have gone on to very successful jobs in industry and academia. And so seeing them and meeting them after many years and seeing how they grow and they make their own careers and they make their own achievements is clearly the best reward one can get from all the effort we put. And Ian knows, right? Because we work day and night, Sunday and Saturday and everything. But when then you get these returns, then you think it's worth it, right?
Thank you so much. Thank you for sharing all this. Ian?
Thanks a lot again, Michele. It's really fantastic. And you see, Alessia, we have excellent speakers. They're all fantastic,
Absolutely.
right? One better than the other one.
Absolutely.
Thank you, Michele, really.
Thank you. Thank you
Thank
all.
you so much for
So
participating,
we'll
for
be in touch.
contributing.
And we thank the audience. And next week we have another speaker, Emil Björnsson from Sweden. So we cover all the geography and all the areas.
Yeah.
So thank you again. I wish you a nice evening.
Goodbye. Good evening.
Yes. Bye-bye. Ciao.
Thank you very much. Bye-bye. Thank
Bye-bye.
you.
Ciao.